Hello, this is Patrick O'Shaughnessy, and this is the 21st module in the series Statistical Methods for Analyzing Data Obtained in the Lab or Field. And this is the fourth part in the series on laboratory statistics, in which we'll focus in on comparison of instruments. So instrument comparisons occurs fairly often in labs. You may need to compare them because you bought a new one and you want to know how it compares to an old one. Or you're in a group of different labs and you want to know and make sure that everyone in each lab is analyzing the same analyte in the same way. So that is the issue here, and how do we go about that statistically? Okay, so based on information you've learned in this series, going back to Module 10, for example, and the statistical test and the associated Module 11 and 12 on T-tests, you might say, hey, I've got two instruments. I can take measurements from both, and I can compare them using T-tests. Okay, so under the scenario that you give kind of random amounts of whatever to one instrument and then random amounts to another instrument, you could then use a two-sample t-test to compare those two instruments. But it would be better, wouldn't it, if you compared each instrument side by side, so to speak, right? They're measuring exactly the same thing at the same time, or they're given the same standard. Now you can use a paired t-test, which would be a much better way to interpret the differences between the two instruments. But, as it says here, however, we don't expect them to be different. They're two instruments that are designed to do the same thing, to measure the same thing, the same way, the same technology. We want to see how close they are together, not how far apart they are. So you would expect that the null is not rejected. Now recall again from the previous modules that not rejecting the null does not state that the means are the same. You can't say that. If you reject, you can say, yes, I'm 95% confident that they are different. But again, if you don't reject, there's nothing you can say about them. Just like in the jury analogy, you can say, yes, the defendant is guilty, but in the opposite sense, you can't say that they are innocent. All you can say is they're not guilty. We don't know if we just don't know. Same thing here, you don't know then if you do not reject. So this gets a not recommended indication here of using a t-test for this comparisons, even though it's highly intuitive and done quite often. Okay, another possible method is to utilize the information given in Module 4 when you're dealing with correlation. You say, oh, that's right, these two instruments should be their output should be highly correlated. So if you give low amounts and increasing amounts to both, they should fall on what you can imagine, right, is the one-to-one line. So here's a graph, for example, of some data obtained from instrument A versus instrument B, and yes, there's some bounce back and forth. They're not perfect, but they fall on the one-to-one line very nicely, and so wouldn't this be a good way to compare them? Let's take a look at this a little bit more. So first of all, the R value we got out of this was 0.996. Wow, that's really close to 1. So we know that there is a strong linear relationship between them, but again, we expect it to be, right? We can also do a test on R, and again, we would expect to reject the null, which is R equals 0. Of course it's not 0. It should be very, very close to 1. And we expect, again, a high R. And not only that, but we will certainly get a high R value, and they will form a straight line even if they're at some other slope, which would be a bad thing if, again, they're lining up like this, and instrument A is always higher than instrument B. We would also get a high R and very significantly different from 0. So again, correlation analysis is nice graphically to show show that they line up pretty well, but from a statistical standpoint, it's not recommended. All right, then let's try regression analysis instead of correlation analysis. We have two analytical instruments. Again, same exact issue here, given multiple standards over a range and compared by a standard, in this case by regression analysis. So now we have the same plot, except we put a linear regression through it. And now we have the ability to look at R squared instead of R. And we can also see that the slope, which we didn't have before, is very close to 1, 0.9536. So isn't that good enough evidence by itself? And again, this is commonly used. Here's the output from the data analysis tool pack. And kind of go through this a bit. Again, the R squared is extremely high. But again, we don't care that instrument A influences the variability of instrument B. That's what R squared tells us. So R is actually a better value to look at than R squared when you're comparing instrument A to instrument B. So again, not interested. So can't really go there. Now what about the slope? And it's very close to 1, again, which is good. And you could look at the p-value on it, which again is a test as to whether beta 1 is equal to 0, which again, we would expect it to be nowhere near 0, therefore not much information there. So maybe we could look at the confidence interval, and this is actually done, and it's not a bad way to go. It's to state that the slope is not significantly different from 1 because, again, the 95% confidence intervals bound 1. They go from 0.88 to 1.02. So you could state that they are not significantly different. But again, this gets back to the same problem as the t-test, that you are using a hypothesis test in a situation in which you do not reject the null. Lastly, you can look at the intercept, and in this case, you do not reject the null either. Here is a p-value of 0.9, which again can be considered a good thing, that there's no significant bias. You can't distinguish the intercept from 0 statistically, and therefore you could state that there is no bias. So this is not again a total reject of a methodology. You could incorporate both those concepts of the intercept is not significantly different from 0, therefore there's no bias, and you could say that the slope statistically bounds the value of 1, which is the goal of instrument A relative to instrument B typically. Now, these problems, as I'm bringing up here, have been considered obviously by statisticians over the past, and one approach that tries to get around this problem is the use of what's called the bland Altman plot. So it's a method that relies on analysis of the difference between the paired samples rather than their correlation. So they ultimately come up with a level of agreement, is the word. Do the two instruments agree with one another, rather than are they highly correlated? So that's the idea behind the bland Altman plot. So in order to set up the plot, you need an XY values, and the X values, so you're going to take every pair, instrument A and instrument B, were both measured at the same time, kind of like a pair t-test, so they are directly comparable. But which one do you plot as the X value? They kind of punt here, they being Bland and Altman, and take the average of the two. Okay, so we're going to make up this X value of A plus B divided by 2. The Y value, again, is their difference. Okay, then much exactly like a control chart, except using 95% confidence intervals, you can establish these intervals about the Y's to determine a kind of a range within which you expect this population of differences to exist. And they should be randomly distributed in order to apply this confidence interval equation, where 1.96 is the 95% confidence z value that's applied to the standard deviation. Okay, so what does this thing look like? Well, let's go back to the correlation plot. You can see there was some variability, right? But instead of, again, correlation, we're going to be looking at these differences between the x value and the y value for each pair. And it'll ultimately look something like this. So the mean of these differences, a minus b, ended up being 0.23. You assume, of course, it's going to be somewhere around 0. It's the whole kind of point behind a Bland-Altman plot. So here's the 0 line, but it's never going to be exactly 0. It's going to be floating above or below it somewhere. And then again, you can establish these confidence intervals, which truly delineate 95% of the area of the normal distribution established by all these points. So now it's, how do we interpret this? Well, one way to do it is to say, you ask yourself the question, is it okay, is it acceptable that our two instruments kind of disagree with each other between those limits? Is it okay that they are somewhere, these values between minus 0.35 and a positive 0.82? So the suggestion then is to first establish what you decide is an acceptable amount of disagreement in order to call them in agreement. So for this particular set of instruments, perhaps you could say that first of all, if they differ within plus or minus 1, right, then I'm going to call them in agreement. And so that is the case here, where even the 95% confidence intervals are within plus or minus 1. Therefore, again, you just establish this boundary a priori, and then go about doing this to determine that you're in agreement to that level, which is kind of interesting, isn't it? Because again, they're never going to be 0. The difference is never going to be 0. So what is an acceptable difference is the idea behind the Bland-Altman plot. And lastly is a concept called equivalence testing. So yes, again, the statisticians have mulled over this problem from the standpoint of going back to a t-test and saying, how could we flip this around? I want to reject when they're the same, right? Instead of reject when they're different. So that's kind of the fundamental aspect of equivalence testing. Again, they're never going to be exactly 0, their difference. So again, just like a Bland-Altman plot, the idea is to first of all determine some sort of difference that is good enough or acceptable to state that they are equivalent. If their difference is this narrow, I'm going to call them equivalent, because again, the difference can never be infinitely 0 in a sense, collapsing down to 0. That's impossible. So what little bound am I going to put around them to say, yep, that's good, that's close enough, they're equivalent. So now we need to set up the statistics for this. And it works like this. Ultimately, we need to say that our differences, again, mu1 minus mu2, are greater than some lower bound, delta lower. See, we're going to reject if they're greater than some lower bound, and we're going to reject, at the same time, we're going to do another one-way test and reject if they're less than an upper bound, to squeeze them in within this zone around 0, actually, that we're going to say is good enough to call them equivalent. Okay, so this is what, I guess, graphically you're setting them up. We know that the mean is going to be somewhere floating around 0, but we want them to be within this delta L and delta U, and by them I mean the confidence interval is within that range. So again, it's very similar to the Bland-Altman plot in its kind of theory. Okay, putting this concept into practice, again, in terms of a confidence limit approach, which is graphically more appealing than trying to do this as a t-test approach, which also can be done. But first we're going to do the confidence interval. by determining, again, the lower confidence limit and determining whether it's greater than or equal to delta L, that predetermined equivalence range. And as we can see here, yes, it is. So we passed that test. And then go ahead and do the upper confidence limit and determine whether it is less than the upper delta. And again, here it is. Therefore, we can state with 95% confidence that the mean difference between our two instruments is within these kind of equivalence range that we have predetermined, and therefore we can call them equivalent. Here's a specific example given in a document by the folks at NIST, N-I-S-T. You can see the URL for it down there if you'd like to pull it up yourself. They give this example of a radiation detection instrument that is tested to determine whether it has this pre-shock reading, as they call it, and are they equivalent to a post-shock reading. And they decide on an acceptable difference, as you see here, of 15% of the pre-shock readings, which is 4.575 relative to this mean of 30.5. So they have then established lower and upper bounds, these deltas of minus 4.575 and positive 4.575. And that may seem like a rather large difference for you in terms of calling it equivalent, but that's all kind of the knowledge of your instrument. You may be down to wanting to be plus or minus 1%, or who knows, but it's one way to calculate the deltas in reference to the mean of say, one of the two samples. The other warning here is that in doing this equivalence testing, you are doing t-tests. And so the fundamental concept behind a t-test is that you are able to obtain normally distributed random samples. So this is not the same as the previous examples given, where it was more of a correlation analysis, right? Instrument A versus instrument B, where the instrument A measurements were allowed to extend over quite a bit of a range, right, in order to establish that linear relationship. Okay, but if you do that on purpose, you will be extending the standard deviation of those measurements quite a bit, and you won't be able to tell them apart with a t-test, and they don't really constitute a random sample. So in this case, you have to have this scenario in which, again, you're, for example, pushing the same standard at instrument A over and over and over again, and getting slightly different readings each time, right? Say maybe do it 10 times, as shown here, there's 10 different samples, and then do the same thing, the same standard into instrument B. So that's the kind of sampling you'd have to do in order to do this equivalence type of methodology. So these are the equations needed to calculate one-way confidence intervals for a two-sample test. And as it says here, there are two of these two-sample one-way confidence interval equations. And that's necessary because, again, they are independent of each other in a sense. If you go back to Module 11, you'll see that the equation for a one-sample confidence interval is y bar plus or minus t alpha divided by 2 times the standard error, this s divided by square root of n. But with a one-way confidence interval, it's more rigorous to state them independently of each other. So we have the positive confidence interval here. And the big difference between a two-way confidence interval and a one-way confidence interval is that we are applying all of alpha to one side of the distribution, so to speak. So we're determining this confidence interval based on t of alpha, not t of alpha divided by 2 as commonly done. And again, we have the lower confidence interval established the same way. And because these are two sample situations, we have to pool the standard deviation. And as you can see, that's the equation down here in order to, you can see it's kind of a weighted mean of the standard deviations of the two different samples that we have. So with those equations in hand, we can then solve for our situation we have here. You can see, first of all, the mean difference, the y bar A minus y bar B was exactly 1, as shown here, and then applying this confidence interval for the negative side, we ended up with 0.51, and the positive confidence interval was 1.48. So we go ahead and plot those on a line here just to make them visual. You can see that the LCI, again, is very close to, in this case, the mean, as is the UCI, in relation to how the deltas were established. We're way out here at positive 4.575 and negative 4.575. So again, we don't want to think of these as being plus or minus in a sense. We are independently looking at the LCI relative to the negative delta, and yes, it is larger, therefore we reject. And likewise, we look at the UCI relative to the positive delta, and it is less than it, therefore we reject. And we can then state that these two situations of the pre-shock and the post-shock are equivalent relative to the pre-established values of the deltas. Now you can also look at this and go, wow, I could have squeezed deltas down much closer here and still have passed. But that is something, again, that maybe is something to be debated with your boss or whatever down the road. But strictly speaking, from a statistical standpoint, you kind of stick with your pre-established deltas as the thing you're doing the test against. And so that is equivalence testing, and that concludes these modules.